Hello everyone and welcome to your lesson of physics. In this video I'm going to solve the assessment of the section of current electricity. And for this one I'm going to start off with the question that most of the students find slightly problematic, which is number dash 4, this one. So we will start off the assessment with this question. Highlight the loop first. Before I do anything, let me highlight the loop of the question. So this is the loop that they are referring: H to B, and then B to J, and then J to F, and then F to G, and then from G all the way back to H. So this is what we have, and in this loop you have to apply the KVL. So before I do anything, okay, we'll solve the question in sequence, but it's just for introduction. Before I start solving the question, let me point out the currents that would be passing through different parts of this loop. For example, this current is I1. We can just see it from there. This current is I1. Likewise, the current from B to J is I2. Okay, and then before we mark any other currents, let us read through the statement. It reads a second cell EMF E2 and internal resistance E2. Okay, but this statement is more important. The uniform metal wire of total resistance R2. So if you consider the total resistance from B to F, the total resistance would be R2. And the thing is, if we break it down, the connection J is halfway along the wire. What does that mean? It means from B to J, the resistance would be half of R2, and then from J to F, the resistance would be half of R2. And then if you combine these two, then you get the total resistance of R2. So if I draw the circuit for this one, if I just convert it into the circuit containing the resistors and all that, it will look something like this. Alright, so I'm not going to draw the lower loop, I'm just going to draw the upper loop. This is B. So B is from B to J, the portion of the wire has resistance R over 2, R2 over 2, half of R2. And likewise from J to F, let's call it point J, and this is a point F. From J to F, the resistance is once again half of R2, and then the circuit is completed. This is point G, this is point H. The EMF is E1, the internal resistance is R1. So let me mark the currents that would be flowing through the circuit. So the current that goes, and this collectively is your battery. Mark the battery first. So the current that is coming out of the battery is I1. It is mentioned in the question. It is I1. Likewise, the current that goes through the part of the wire B to J is I2. Again, it's given in the question. I2, you can see over there. But then the tricky part is, and this is what many of the students would assume, that the current in the entire wire is I2. They'll say the current flowing through this one is also I2. So current, if I refer back to the original diagram, the students would assume that the current through J to F is also I2. But the thing is, if you say this current is I2, over here it is I2, the same current I2 over here, the same current I2 over here, the same current back to the battery would be I2. But then you would come to a problem. The current that was drawn from the battery was I1. The current that was coming out of the battery was I1. But the current that enters back to the battery is I2, which should not be the case. If the current coming out of the battery is I1, then the current going back to the battery should also be I1. This is the most important pointer. And by this information, you can trace all the currents backward. So current out of the battery should equal current into the battery. These two currents should be equal. If you get I1 from the battery, from the positive terminal of the battery, then what goes to the negative terminal of the same battery would also be I1. So it should be I1 over here. So what we do, I'm going to trace it backward. Let's trace it backward instead. So if this one is I1, the current coming out of the battery is I1, then the current that enters the battery would also be I1. And then the current, if I trace it all the way back, it would also be I1 because there's no deviation in the current up till now. It would also be I1 because there's no deviation in the current up till now. There are no branches, there are no different paths, so the current would remain same I1. And the current that would flow through here would also be I1. The current that goes through here would also be I1. But this is a point where the current was divided. So behind J, behind this point, the current is no longer I1. It is I2. And makes sense because up till this, in this part, from here all the way till here, there was no deviation in the current. And exactly at point J, there is some deviation in the current. So the final conclusion is the current that flows through first half of the wire B to J, current from B to J is I2, but the current from J to F is I1. Now this information would be very useful to solve part B, part 2 and part 3. So let's follow the sequence, and we start off with the first one. Use Kirchhoff's law to obtain the relation between the currents I1, I2 and I3. Let us start off with this one. You can choose any junction, whatever junction is most convenient in that case. For example, if I choose the junction B, I can easily relate the three currents in the junction B. So can you help me out with the expression of the currents at the junction B? I1 plus I3 equals I2. I1 plus I3 equals I2. Now check out the next part. You have to use the Kirchhoff's law to obtain the relation between E1, R1, R2, R1, I1 and I2 in the loop HB, the highlighted one, the upper loop. Okay, so in this one. And I'm going to raise up this stuff, at least for now. And it will look something like this. So we're going to go with the second method, in which we write EMFs on one side and we write PDs on the other side. So I'm not going to go with the first method. I'll rather go with the second method. And in that one, we simply write EMFs on one side and we say sum of all the EMFs would equal sum of all the PDs. And luckily, in the loop that we have marked, we only have a single source of EMF. So there would be a single EMF on left side, which is E1. So E1 equals. Other than that, we have the PDs, the potential drops. And the standard direction of current is the green one from positive of the battery towards the negative. All the currents that are aligned with the standard direction of current would be positive. And if there's an opposite current, that would be taken as negative for the potential drops. So let us write the potential drops. So the easiest one is you start off with the point, let's say point H. You start from here, from the point H. You walk over here. Up till now, there's no potential drop. But as we move from B to J, as we move through that part of the wire, there would be some voltage drop across that part of the wire. How much would that be? Current times the resistance. Why I2? Because I2 is the current passing through B to J. Why resistance is R2 over 2? Because the total resistance from B to F was R2, sorry. And the resistance from B to J would be half of it, because J is exactly in the midpoint. So we are done with this part. And then the next voltage drop occurs at cross J to F. so which is also a resistance. So this thing plus I1 and half of R2. This is the voltage drop across the part of the wire J to F. Why I1? Because the current passing through that part of the wire is I1. And matter of fact, I explained it already that if you trace the currents backward, you know that the current passing through J to F from that part of the wire is I1 and it's not I2. And we're done with this component also. And finally, we have a component over here, R1. And what is the voltage across it? Well, that equals to I times R. And finally, we have the small internal resistance, and the voltage drop across that one would be I1 small r1. So how many PDs? You can do a counter check for the PDs. We have a total of one potential drop over here, the other one over here, 2, and then the third one over here, and then the fourth one over here. 4 PDs. There should be 4 terms on the right side. So what do we get for the final expression? We get E1 equals to I2 R2 over 2 plus I1 R2 over 2 plus I1 R1, the capital, plus I1 R1, the small one. So this is what we get for the first one. I'll just copy paste over there. So now let us consider the loop H, B, C, D, J, F, G, H. So I'm going to erase off everything else from here so we can concentrate on the given loop. So we have to consider this loop. You have to start from H all the way back to H, but we gotta go from the lower side. Given loop is this one. This is a given loop now. And once again, as I have marked the currents already, the current, so this one is I1 over here, and so the lower part, the current is I2. I3, as you can see on the diagram itself. This is the loop that we have to refer to. All right, so in this one we have 2 batteries, so we have to take one as a reference. So I'm going to take E1 as reference, and I'll be setting the standard direction of current as this one, because depending on that battery, the standard direction of current is this. And forget about the central part B to J. This is not even part of the loop. Okay, so this thing is I2 is not even included. So let us write down the expression. EMFs on one side, PDs on the other side. EMFs on one side and PDs on the other side. So sum of all the EMFs equals to sum of all the PDs, potential drops. So the first EMF, the chosen one, is E1. And then we have E2, but E2 would be written with the negative sign. Would be subtracted from the first one. And the reason being, because positive in front of positive, the voltages would be subtracted. This is what we study. Matter of fact, we study from O levels, the combination of batteries in series. If they are combined, positive, negative, then positive, then negative, the batteries would be added, but same terminals joined together, the batteries are subtracted. And that's it from the EMFs. So let's see what do we have from the PDs. So well, we have one of the PD we'll have over here across this resistor, then across this resistor, then across this resistor, and then across this one. So 1, 2, 3, 4. There'd be 4 PDs. And let us start off with the first one. If we start walking from this side, then the first one that we encounter would be through R2. The potential difference across R2. In that case, it would be minus I3 times R2. And you would know the reason for the negative sign, because the standard direction of current, the red one, which is anti-clockwise, and the direction of current I3 is opposite to that. So I3 is kind of clockwise. The standard direction is anti-clockwise. So up next we have to go cross J to F, which is the resistance, which is part of the wire, and the voltage drop across that one would be plus I1 times half of R2, because current passing through that one was I1. And once again, why current passing through that part of the wire is I1, trace it all the way back. Then plus through this one, the potential difference would be I1 times capital R1, and then through the last one it would be I1 times small r1, and that would be it for this one. And then you have the next one, which reads the junction at J is moved along the wire. Explain why the reading on the ammeter changes. So junction J is moved along the wire means they move it probably to the left side, to the right side, and the reading on the ammeter changes. So the thing is, as you move the junction along the wire, due to that, the potential difference across B and J would change. And the potential difference, due to the change in the potential difference, the current passing through the ammeter would also change. So I'm just going to write the bullets and you can write in description. So let us consider the next question that we have over here. A wire has length 100 centimeters and diameter 0.38 millimeters. The Main Law of wire has resistivity that much. Show that the resistance of the wire. Okay, so easy one. Resistance equals to rho L over A. Then resistivity is 4.5 into 10 to the power negative 7. The length is 100 into 10 to the power minus 2 divided by A, the area. The area can be obtained from the diameter by d squared divided by 4. And the diameter is 0.38 into 10 to the power negative 3. And then square of it. Because we have to compensate for milli also. We had to compensate for centimeters and then we had to compensate for millimeters as well. So what do? We just hit it on the calculator as it is. Okay, so 4.5 into 10 raised to the power minus 7 times 100 into, I could have written it as 100 into 10 to the power minus 2 would be would be 1. Because 100 centimeters, you can simply say 1 meter. So you don't even have to write the prefix with it. But in the denominator, we have pi by 4. Pi by 4 times 0.38 into 10 raised to the power 3. Bracket closed, and then square of it. And the other bracket also closed. So what do we get? We get 3.967. As you can see on your screen, we get 3.967, which is also known as 4.0 ohms. So for the part B, this is a question from the potentiometer. So let's see, what do we need to find before I read the entire question. The galvanometer, we don't even have the galvanometer, but the current in the cell Y is 0. So that means no current flows through this part. And the only possible way no current flows through this part would be if the potential difference over here equals EMF of the battery. If no current flows, then we can say the voltage across BC equals EMF of the lower battery, which is 1.5. EMF of the lower battery, let's call it E2. That would be E2. And we can say the voltage across BC is also 1.5 volts. So we know it's 1.5 volts across BC. We need to calculate the current in the cell X. So for this one, if you know the resistance of any component in this series circuit and you know the voltage difference across that component, you can easily find the current. So if I raise it off, at least for now. So in this circuit, if you know the value of potential difference across any component, and you know the resistance of that component also, you can find the current through the whole circuit. Because it's a series circuit, current remains same everywhere. So the thing is, current in the cell X. Okay, so what we need to do is we need to find the voltage, which is 2 volts. Okay, for let's say for the upper loop the voltage is 2 volts, and the total resistance of the upper circuit, would be, the resistance of the wire would be taken as 4. So the resistance of this whole wire would be taken as 4 ohms. So if I redraw the circuit, you can think about the circuit like this one. So you had a cell over here, and then you just have the wires, and the first resistor, which is basically a wire, is 4.0 ohms. We calculated in the previous part. And then the internal resistance has the resistance 1 ohm, and that's it. You simply need to find the current through this circuit. And if you find current anywhere in the circuit, it'll be same everywhere. So the total EMF is 2 volts. And if you're using the total EMF, you have to consider the total resistance of the circuit. So current equals to, if you use the total EMF, which is the total voltage, then you have to divide the total resistance. So 2 divided by 5, which is 0.4. And in 2SF, you can write it as 0.40 amperes. Okay, so then you need to find the potential difference across the wire BD. So it does not get easier than that. Potential difference across this wire would be V across BD would equal the current that flows through it, which is 0.40. We just calculated the current, times the resistance of the wire. Resistance is 4. Where did we calculate? In the previous part. In the very first part, we calculated the resistance of the wire BD. So 0.40 times 4, it would be 1.6. And then the last part, the distance L, which is actually the question of the potentiometer now. So we need to find the distance L, this one. So very simple. We'll use the ratio method, our favorite one, in order to solve these sort of questions. We have voltage on one side, we have length on the other side. So the total voltage across the wire BD was 1.6. So 1.6 volts were provided. Length is in centimeters, right? Centimeters? Yes, centimeter. So 1.6 volts were provided to the wire BD, which had the total length of 100 centimeters. As you can see, the wire has length 100 centimeters. So 1.6 volts are there for the length 100 centimeters. And the voltage across B to C is 1.5. And for what length? For X length. So if across 100 centimeters, you have 1.6 volts, then across what length? You'll have 1.5 volts. And how do you know that voltage across B to C is also 1.5? Because we study that in potentiometer. If no current flows through this portion, through the lower circuit, then the EMF of the battery and the voltage across this part would be same, because these 2 points would then be parallel to each other. The 2 points would be connected directly. For example, this one, B is connected to positive of the battery and C is connected to negative of the battery. The internal resistance is not even used in that, because there is no current passing through the circuit, and hence this resistance is redundant, of no use. So if we cross multiply, I'll be getting 100 times 1.5 divided by 1.6. Then I'll hit it on the calculator. So you get 150 divided by 1.6. You get 93.75. We'll round it off to 2SF, we'll get 94 centimeters. And then you have the theoretical one. They always end up the question of potentiometer with the similar question. The connection C is moved so that the length L is increased. Explain why EMF of the cell Y is less than its terminal potential difference. Now, first of all, as you change the length, there would now be current in the lower circuit. So in this circuit, there would now be current. And some of the voltage would now be lost against internal resistance as well. So we'll no longer say that this resistance is redundant. Matter of fact, this resistance would have some significance in the circuit, because now the current flows through it and there would be voltage drop across this one. So then you can phrase it by yourself, but I'm going to write the important point. As length L is increased and flows through the circuit, through the lower circuit, energy is lost due to internal resistance. Okay, just phrase it properly. Do not use the symbols, rather use the full letters, full words. Okay, so this is just the first part, nothing to do with the potentiometer. You need to calculate the current in the cell X.